Hey guys, welcome back to chapter 4. What we're going to do now is talk about exceptions to the rule. So, in the last lecture, we talked about binary ionic compounds and we stuck to just the main group elements that were very predictable. Now, what we're going to do is we're going to introduce two exceptions to the rule. So, first is going to be our transition metals, and then something called polyatomic ions. So transition metals tend to form more than one type of ion. So if I look at iron here, it can be a +2 or a +3. Nickel, 2 or 3. Gold down here can be a +1 or a +3. So there really is no rhyme or reason or easy way to predict which type of ion is going to form. So when we go writing the names of these compounds, or when we go writing the formulas, we've got a little bit of extra work. We've got to tell the viewer something extra about this compound. The way that we're going to handle these multiple charges is when we write the names of our metals, we're going to put a Roman numeral after the name. That Roman numeral is going to tell the viewer what the charge is on that metal. So if I were to write iron and then the Roman numeral 3, I'm telling the viewer, they don't have to think about it at all. I'm telling the viewer, hey, it's a +3 charge. If I write tin 4, I'm telling the viewer, hey, don't think, it's a +4 charge. Okay? So Roman numerals are going to be the way that we communicate what the charge is on that ion. So let's look at an example here. So writing the name of these compounds should look very, very similar to what we've done already. We're going to keep the name of the metal, so we're not going to do anything to that. Jump over here to the green box. We're going to keep the base name of the non-metal and add IDE. That's all the same. The only new piece here is we've got to include Roman numerals when we're talking about transition metals. So we only use Roman numerals for transition metals. That's it. So here I see two compounds with copper and chlorine. Both of these compounds are perfectly acceptable compounds. They both exist in real life. But when I write the names of them, the names are going to look pretty different. Okay? So for the first one, let's first write the name of our metal. So what is the metal we're dealing with? Cu. So I'm just going to write copper. Okay. Then I'm going to write the base name of my non-metal, and I'm going to add IDE. So Cl is chlorine, so base name is chlor, add IDE, chloride. And I left this space in the middle, okay? Now I have to tell the viewer what the charge is on that copper, because it could be a 1, it could be a 2, it could be a 3, but I need to tell the viewer what it is. When we look at these compounds, we're going to assume that they are neutral. They're electrically neutral, okay? I don't know what the charge is on copper because it can change, but chlorine is a main group element. Chlorine always has the same charge. So chlorine is in group 17 or 7A. It's got 7 valence electrons, so it's always going to steal 1. It's always going to have a -1 charge. Okay. If this is an electrically neutral compound, and it is, what must the charge be on copper in order to balance out that -1 from chlorine? Yeah, it's got to be a +1. Okay, so 1 copper with a +1 charge, 1 chlorine with a -1 charge. That's electrically neutral. So I'm going to tell the viewer that, hey, the charge on this particular copper is 1. And the way we read this is copper 1 chloride. Okay, let's come over here to the other side. I'm going to change colors. All right, so again, this compound exists, right? So I'm going to write the name of the metal, still copper. I'm going to write the base name of the nonmetal plus IDE, still chloride. And I still recognize copper as a transition metal, so I left a space there. Okay. All right, so this particular formula is also electrically neutral. So again, chlorine is a main group element, and it's got a charge of 1-. But what's the difference here? Yeah, there's 2 chlorines in this formula. So if each chlorine brings a -1 to the table, and there's 2 of them, there's a total of a 2- charge from the nonmetal. We've got 1 atom of copper. So what must the charge be on that 1 atom of copper in order to balance that -2? Yeah, this copper has to be a 2+ charge. Okay. So 2 chlorines, each with a -1. We need a copper with a +2 charge. The way that I would tell the viewer is I put a Roman numeral 2. And we would read this as copper 2 chloride. Okay. All right, so let's work on another example. Why don't you guys go ahead and pause the video, see if you can write the correct formula for this ionic compound, and then hit play and I'll walk you through it. All right, so first step is to get the chemical formulas onto the paper. So the formula for iron is Fe. The formula for oxygen, well, oxide, which is oxygen, is O. Okay. The next step is the equivalent of showing your work. So this step is not necessary, but it certainly is very helpful in the process. Okay. So what is the charge going to be on iron? Well, the one thing I like about transition metals is I don't have to think about it. It tells me, hey, it's a Roman numeral 3. Don't think. The charge on iron is a +3. I don't have to think about it at all. I like that. Oxygen. So oxygen is a main group element. Oxygen has 6 valence electrons. So it's going to steal 2 to get to 8. So it's going to be a -2 charge. This is the first one we've seen where one of the charges hasn't been a magnitude of 1. Okay, we have a 3 and we have a 2. So at this point, you could find the least common denominator, figure out what charge both of them could have to balance out, and then determine how many of each you would need. That just sounds like a lot of work. So let me give you a little helpful hint here. It's got a very scientific name. I call this the flippity flop rule. So what's going to happen here is the magnitude of one charge is going to be the subscript for the other atom. And the magnitude of this charge is going to be the subscript for that atom. So the formula for this would be Fe2O That would be the correct formula. Okay. Now, everything I tell you, especially when I name it the flippity-flop rule, you should question everything that I tell you. So let's make sure that this works out, that it balances out, okay? So iron. What is the charge on each atom of iron? Yep, each atom of iron has a 3+ charge. And according to the flippity-flop rule, how many atoms do I have? Yep, I've got 2. So 2 atoms, each with a +3, is going to bring to the table a +6. Let's do the same thing for oxygen. Each atom of oxygen has what charge? 2-. And according to the flippity-floppity rule, how many oxygens should I have? Yep, I should have 3 of them. So 3 atoms of oxygen, each with a -2 charge, is going to give us a -6. +6, -6. That's electrically neutral. So flippity-flop does actually work. So now that I've proved to you that it works, you can use it. Okay, it's certainly something that you'll want to use. And again, if you don't quite trust me, it is in your textbook. So this is a graphic from your textbook showing the same flippity-flop rule with the binary ionic compound. So if we just have a regular main group element coming together with a main group element, it still works. All right, so that was transition. So we introduced the idea that transition metals can have multiple charges. We introduced that we have to tell the viewer what the charge is using Roman numerals. And then I helped you with this flippity-flop rule. Let's talk about the other exception to the rule now. The other exception to the rule is something called a polyatomic ion. So let's break that down. Poly is the prefix for many, atomic, atoms. So many atoms coming together. So it consists of more than one atom. Those atoms are covalently bonded together, and these are polyatomic ions. What's an ion? Well, that's a charged particle, right? So these are groups or packets of atoms that come together, and for whatever reason, this packet of atoms carries with it a charge, okay? So here is just a table of common polyatomic ions from your textbook. So the polyatomic ion nitrate, for example. Here's nitrate. Nitrate is a package of NO3. That is nitrate. If you change this 3 on oxygen or you change the implied 1 on nitrogen, it is no longer nitrate. So nitrate is 1 nitrogen, 3 oxygens. Okay? So very often when I'm working with these, I'll put parentheses around them to remind me that that's a package. This package carries with it a charge. So this package has a -1 charge. Let's look at another packet. Let's look at carbonate. So up here is carbonate. So carbonate, the package carbonate is 1 carbon and 3 oxygen. That is carbonate. This packet has a 2- charge, so it carries with it a 2-. Okay, so this packet is called carbonate, and it's got a -2 charge. With these being ions, charged particles, they are able to participate in Ionic bonding, right? So they can share, they can transfer electrons and come together. So let's look at the compound between magnesium and nitrate, and then we'll name it. Magnesium is a main group element. It will always form a positive 2 charge. Nitrate is one of our polyatomics. So we look at our list, we see this packet of atoms, and we see it has a -1 charge. So when these two compounds come together to form a molecule, we can use our flippity-floppity rule still, right? So this 2 is going to be the subscript on nitrate. This 1 is going to be the subscript on magnesium. And that would give us an electrically neutral compound. So we're going to write magnesium. And then nitrate. Remember I said that nitrate is NO3. If I change this 3 right here to anything else, it is no longer nitrate. You're saying, though, Miss Maz, I need to have a subscript. When you put a subscript, what you have to do is put this in a package, and you have to put the subscript on the outside of the package. So what this subscript is telling me is I need 2 packages of nitrate for every 1 atom of magnesium, okay? Here is a common error, and I'm going to put it in red because it's wrong. Students will look up here and they'll say, okay, 2 is the subscript, so it's NO2. Wrong. What is this compound? This is magnesium, and if it's attached to NO2, that's not nitrate anymore. What is that? It's over here, it's nitrite. So by writing NO2, you've completely changed what compound it is that we're dealing with. So again, just to review, magnesium, nitrate, and put it in a package and put the subscript out here. Okay. Naming polyatomic ions is really, really easy. To name compounds with polyatomic ions, we're still going to write the name of the metal. So we're going to write magnesium. And when we're going to write the polyatomic ion, we don't do a thing to it. We just simply write down the name. So NO3, I come over here to my chart, that's nitrate. And I'm going to write it down here just because I ran out of room, but nitrate. Okay. So the name of this compound is magnesium nitrate. Okay. If I can clear this off. There we go. And then I went through all the same process. Okay. So those are the exceptions to the rule. These are where things start to get a little bit tricky. So again, now is a great time to pause and practice ionic before we get into covalent. Because when I add covalent on top of all of this, that's when things start to get a little bit trickier. Okay. Hope you found this helpful.